Welcome everyone. My name's Richard Victor Vishesh. I am from the Department of Tripoli at American International University, Bangladesh. The title of our accepted research paper on ICICTD 2022 is a waveguide fed hybrid graphene plasmonic nanoantenna for on-chip wireless optical communication. The authors of this paper are Richard Victor Vishesh and Faradun Arifi. The contents of this presentation are as follows: introduction, problem statements, related works, research questions, objectives, methodology, simulation results, conclusions, future research directions, references, and acknowledgements. So without much further ado, let's begin this presentation. Integrated circuits, that is ICs, are the heart and brains of all the electronic designs. Therefore, they can be found in today's computers, CCTVs, cameras, automated equipment, automobiles, smartphones, game consoles, digital cameras, data centers, and so on and so forth. All ICs can be categorized as analog, digital, or a combination of the two. So what are the expectations from today's ICs? They must be faster in moving data, efficient, and capable of computing correctly. At the bottom right corner, a Samsung processor embedded in a Tesla car is depicted, where different system on chips, that is SoCs, are routed. Although various metallization layers are employed to interconnect every element to meet delay criteria in gigahertz range. The whole processor needs to be redesigned for high frequency applications, especially in terahertz. That leads to high cost and scalability of wired interconnects, which in turn slow down the processor. Problem statements. The main issue of wired interconnect is its rigidity. That is, it can't be changed over time. Another thing is that memory, CPU, GPU, and accelerator communicate internally with each other through wired interconnect at different frequencies. An addition of an external memory unit may change the overall perspective of different communication patterns. That's why a feasible interconnecting medium should be ensured, which is flexible, versatile, faster, and low cost. In this research work, we are proposing a tunable optical miniaturized nanoantenna as a complement of wired interconnect. With the inner and broadcast capabilities, this nanoantenna can be integrated into the SoCs for inter or intra on-chip optical communications by forming multiple spatial wireless channels. Related works. W. Shetty et al. Proposed a Yagi-Uda antenna for 1550 nanometers optical communication systems. This nanoantenna achieves an impedance bandwidth ranges from 193.37 and 193.71 terahertz at a center frequency of 193.5 terahertz with a high gain and directivity of 12.9 and 16.6 dB respectively. Next, a 3D optical Yagi-Uda nanoantenna array was modeled by D. Dragali et al. A significant difference between the two reflection spectra occurs at 1.5 micrometer, at which the radiation pattern shows the highest asymmetry. The directivity gain and efficiency of this array are 15 dBi, 6 dB, and 33.33% respectively. After that, Noor Mohammadi et al. Proposed the ultra-wide photonic hybrid plasmonic horn nanoantenna with SOI configuration. The proposed nanoantenna has a reflection coefficient of 15.7 dB and a gain of 4.67 dB at the optical wavelengths of 1550 nanometer. Related works. Next, then a hybrid plasmonic waveguide fed broadband nanoantenna for nanophotonic applications was modeled by Dragali et al. From the figure, the return loss and gain of this nanoantenna are -13 dB and 5.03 dB respectively. Next, we have a smart optical cross dipole nanoantenna with multi-beam pattern, which was designed by Moshiri et al. By introducing a cross dipole nanoantenna with two V-shaped coupled elements, the maximum directivity of 8.79 dBi was obtained with unidirectional radiation pattern. After that, an enhanced gain triangular patch nanoantenna using hybrid plasmonic waveguide on SOI technology was proposed by A.K. Branwell et al. The proposed nanoantenna has satisfactorily gained 7.792 dB and S11 of -12.86 dB at the optical telecommunication wavelength of 1550 nanometer respectively. Next, Shetty et al. Demonstrated a dielectric resonator nanoantenna at optical frequency. The simulated nanoantenna achieves an impedance bandwidth of 2.58% and an end-fire directivity of 8.6 dBi, covering all the standard optical transmission window at C band. Then a hybrid plasmonic nanoantenna with the capability of monolithic integration with laser and photo detector on indium phosphate substrate was designed and simulated by Nicoford et al. By using the finite element method, it was observed that this nanoantenna can radiate and receive the optical field with a gain of 6.6 dB and return loss of -22 dB at the frequency range of 180 to 220 terahertz. Lastly, Yusuf et al. Proposed the waveguide-fed optical hybrid plasmonic patch nanoantenna. The proposed device provides a bandwidth of more than 15 terahertz, a gain of 5.6 dB, and an efficiency of only 87%. The research questions are as follows. Which type of miniaturized nanoantenna is best for optical communication? What are the ways to improve the radiation characteristics like S11, directivity, gain, efficiency, and electric field pattern? How to reconfigure an optical nanoantenna for a wide range of visual spectrum. Next, how to obtain practical dynamic and local biasing if graphene is used. Lastly, how to encapsulate graphene to achieve the necessary mobility to create such nanoantenna. Objectives. The objectives of this research work are to implement an efficient, faster optical transceiver system instead of the existing high latency systems operating at radio frequency, microwave, and millimeter wave frequency. To avoid purely metallic nanoantenna, as a lot of power is required for it to operate at optical spectrum. Then to model a hybrid graphene-based plasmonic nanoantenna, which will help us to create an intra or inter on-chip wireless nanolink. Lastly, to tune the nano antenna structure parameters and to optimize the graphene properties such that the true potential of our proposed nanoantenna can be optimized at optical regime. Methodology. To have the optimum radiation characteristics, the parametric analysis of the waveguide-fed hybrid graphene plasmonic nanoantenna has been executed by varying the radiator geometry, size, thickness, metal, substrate, and chemical potential of graphene. Then we can have the improved nanoantenna with better radiation characteristics. In figure A is the initial design of the waveguide fed hybrid graphene plasmonic nanoantenna, having a combination of aluminum, graphene, and silicon dioxide, and waveguide port has been used to steer this thing. So as depicted in figure B, the S11 of this nanoantenna is minus 12.667027 dB at 193.5 terahertz. The directivity gain and efficiency of it are 10.147 dBi, 7.291 dB, and 71.853% respectively, which is not satisfactory. So it's apparent that the radiation capacity of this at the frequency of interest have to be improved further by tuning the antenna parameters. Simulation results. Optimal steps 1 to 3. Let's look at table A first. As compared to other radiator geometries, the W-shaped slots form the radiating structure in such a manner that both electromagnetic field vectors strike the radiators symmetrically, deriving a unidirectional radiation pattern with excellent efficiency of 81.801% and return loss of minus 29.295 dB. As a result, for the imminent optimization steps, radiators designed by the W-shaped slots have been taken into consideration. Referring to table B, the size of our design has been selected between 750 by 750 nanometer square and 1250 by 1250 nanometer square in such a way that the minimum reflection coefficient and good efficiency are apparent. In fact, a size of 1000 by 1000 nanometer square for our proposed nanoantenna has been chosen, which provides much lower radiation characteristics. Sorry about that. The S11 or the reflection coefficient of minus 19.989 dB and excellent efficiency of 84.626% as compared to the other ones. Next, while all the listed thicknesses show comparable return losses, our proposed nanoantenna with a thickness of 207.5 nanometer has been preferred for its remarkable efficiency of 84.626% as shown in table C. Simulation results optimization steps 4 to 6. Take a look at A now at 193.5 terahertz. Since the reflection coefficients and efficiency of silver, gold, and copper are not prominent as compared to aluminum, aluminum metal has been sandwiched between the silicon dioxide layer and the graphene in the radiating structure of our proposed nanoantenna. Then it's clear from table B that silicon dioxide substrate has been used as the graphene plane and one of the layers of the radiating structure because it significantly improves the efficiency as opposed to the other substrates. Then in table C, the last stage of the optimization process, graphene with 0.7 electron volts chemical potential has been considered because such biasing voltage brings forth an excellent nanoantenna efficiency of 92.821% in contrast to other values. Simulation results and optimized nanoantenna in terms of S11 and electromagnetic fields. Here we have the modified layers of various materials such as aluminum, graphene with 0.7 electron volts, and silicon dioxide of our optimized waveguide fed plasmonic nanoantenna at 193.5 terahertz. For our proposed nanoantenna resonating at 193.5 terahertz, the return loss and minus 10 dB impedance bandwidth of minus 28.22 dB and 88.43 terahertz respectively have been achieved as depicted in figure A. In figure B and C, the electric field and magnetic field patterns in the XY plane at 193.5 terahertz are illustrated respectively. Simulation results and comparative analysis, directivity, gain, and E field or the electric field radiation pattern. The 3D far field directivity of the proposed nano antenna is demonstrated in figure A, where maximum directivity of 13.3 dBi has been obtained. In figure B and C, the 2D and 3D far field plots of gain for this nano antenna at 193.5 terahertz are depicted individually. Along the elevation plane, the proposed nano antenna radiates the electromagnetic waves with a maximum gain of 12.4 dB at 1515 nanometer. From 2D radiation pattern, gain lies within minus 30 to 30 degrees. The far field radiation patterns and parametric values of the total electric field in various planes of the proposed antenna are illustrated and accumulated in figure D and table A respectively. At 193.5 terahertz, the proposed antenna emanates unidirectional electromagnetic beams along XZ plane, that is the elevation E plane, with a main lobe magnitude of 27.1 dBi. dBV and negligible side lobe level of minus 18.7 dB. It's important to note from table B that our proposed waveguide fed hybrid plasmonic nano antenna offers considerable efficiency of 93.23% and lowest reflection coefficient of minus 22.22 dB. Conclusions. The outcomes of this hybrid graphene plasmonic nano antenna operating at 193.5 terahertz are as follows. Improved geometry with distinctive W-shaped slotted radiator has been simulated using CST Microwave Studio. Minimum reflection coefficients of minus 28.22 dB as compared to that of the reported ones. Then higher directivity of 13.3 dBi, gain of 12.4 dB, and efficiency of 93.23% has been acquired. Compact footprint of 1 by 1 micrometer square. Then it's simple but costly fabrication techniques will be required, like Talbot lithography, nano imprint lithography, etching, and so on. Because of its excellent radiation characteristics, inter on-chip wireless nanolink for secure optical data transfer with low latency can be realized. Future research directions. Designing a highly directive non-conformal graphene-based MIMO nano antenna implemented in a heterogeneous system on chip network for wireless optical communication. MIMO polarization diversity performance metrics will be checked in terms of isolation or transmission coefficient like S121 or S12. Envelope correlation coefficient, diversity gain, and channel capacity loss. Then fabricating the optimized design and testing it with the vector network analyzer. These are some of the excellent resources to prepare my slides. Acknowledgements. Firstly, I would like to thank Mr. Faradun Arifin sir for guiding and providing invaluable advice throughout this research work. Last but not least, I'm grateful to Dr. M. Tansir Ali, Dr. Muhammad Nasiruddin, Professor Dr. Muhammad Abdur Rahman, and Professor Dr. Abian Siddiq Hossain for giving me facilities to successfully accomplish this research. This is the end of my presentation. Thank you for your time and patience.